Well, good morning, everybody. It's exciting to share with you what's happening in the battery space. The title of my presentation is How Far Can Batteries Go? Far right here has multiple meanings. It can mean how far electrical car can drive per charge. It can also mean how many years it can last. Would you be able to produce a battery that's immortal, can go forever? That's a question we ask a lot. How far can also mean how wide range of applications batteries can impact. So in the next 15 minutes, let me share with you some of the learning over a decade and what could be next. So our battery technology really starts from here. We utilize what's already in electronics. For the cell phone, for the laptops, this is 18650 cell. You open it, you see a cylinder, cut it open with this roll of materials right there, and consisting of graphite particles and lithium metal oxide. So lithium ions are moving back and forth inside the batteries with the electrolyte, with the separator right there, electrons are moving outside. This is a simple device, just two terminals. From yesterday, from Dick Swanson, I was laughing really loud, right? It's a solar cell, it's very simple as well. It's two-terminal device. However, you need to make billions of those. It becomes not as simple as what you think. So starting from electronics, this has the history of about 27 years of battery use in electronics. So this already built up a really good supply chain, reduced the cost to the level. In the past decade also, we started to think about, as a whole society, whether this could be used for the electrical car, for the drone, and for the grid-scale storage. So what we have achieved after 27 years, energy density somewhere about 250 watt per kilo. Can we go to 500? That has a significant meaning right there. Per charge, if you have 500 watt per kilo, that basically means with a normal size battery, you are going to have 500 miles driving range. That's even can exist the gasoline car. So the cell cost, instead of somewhere around a little bit over $100, can you go to half, $50 per kilowatt hour? This also has significant meaning that will allow electric car to be affordable to the general public. The cycle life, we usually have 1,000 cycles, 7 years also. Indeed, my phone, after 3 years, I can already see significant decay. So can we make a nearly immortal batteries that's 10,000 cycles, 25 years or 30 years? That really means after your car retire, you can take out the battery pack and put it into the electrical grid to use it for quite a while. This will help reduce the cost tremendously. In terms of charging, we are usually in the 1 to 2 hours charging range. Can we do 15 minutes? In reality, we really like to go less than 10 minutes. This will allow us to build less charging station to also reduce the infrastructure cost. And the battery so far is not safe. Can we make a completely safe battery? No matter what you do, how you abuse them, they never catch fire, they never explode. We are not there yet. So any of these parameters I show you right here, without sacrificing others, if you can improve the parameters going from the black to the red, that's a huge breakthrough to the whole battery space. So in order to increase energy density, you need to work on materials. So in the past decade, we have been seeing the idea, how do we use silicon and also down the road metallic lithium to replace graphite that store 10 times more charges compared to graphite. And how do we use something like sulfur that's also 10 times higher capacity compared to the lithium metal oxide currently used. Not only is that, sulfur is very low cost. I'm going to come back to that. If we can enable these new materials, we can move from 250 watt per kilo, that's right now, and the next 5 years, we are going to see in the commercial space, this is going to go up to close to 400, maybe 5, maybe 10. I'm giving an estimate timeline right here. Lithium metal coming in combined with the traditional cathode and sulfur. This allows us to go to 500 or more. So we do have materials, we do have the batteries chemistry available to do so. However, it's really challenging. These materials carry a lot of problems we have to solve. So let me share with you one type of the electrode we have been working on for a decade now. It's a silicon. 10 years ago, when we published the first paper, it tried to solve this problem. Silicon absorbs a lot of lithium ions, but the volume expansion is 4 times. Compared to in the past, what we know is we can handle less than 10% of volume expansion. Now you are talking about 400%. We are a completely different regime. How do you handle those problems? At the materials level, electrode level, and the whole cell level, it wasn't clear. So we learned about this from our generation 1 design, that silicon nanowires. This was funded early days by I just joined the faculty, by my starting up fund, as well as the Global Climate Energy Project. And moving to now, up to now, we have 11 generations of materials. Each generation is trying to solve one big problem that's very, very challenging. So 10 years ago, we invented the silicon anode technology. And silicon, and Stanford right here, it's hard not to start our company. So we did try to commercialize this technology. Now we do have the product line on the market. The nanowire-based one already get to somewhere about 400 watts per kilo. We also have the silicon nanoparticle mixing with graphite that gets you somewhere close to 300 watts per kilo. These are the leading products in the market. But the scale up is certainly very challenging. We raised $150 million to get us somewhere. We still need more to go. But let me make a comment along this whole process. This is something I learned. So coming back to that 10th generation of design, it's indeed, in terms of university funding, it's very, very challenging. You can raise funding continuously for a decade to support an idea that can go for such a long time. This combined the support of my startup package, the GSAP, indeed the Chaos Investigator Award. President Xi is sitting right there. He was the one giving me this $10 million award back to roughly 10 years ago. And then later, supported by Department of Energy. So this is a lucky case. We have funding continuous until nowadays to work on silicon to solve all these problems. But all my other projects, I see it's very challenging to do so. If some of the policymakers right here, my feedback to you is how do we come up idea, continuous support energy, and also good idea that's promising continuously without gap. That will be very important. So talking about battery safety, it's not safe yet. Every couple of years, we're going to see major instance right there. What happened inside? You have this anode and cathode. And then either due to your overcharging or you're charging in the bad weathers, or you have manufacturing defect, you're going to create a shorting right there. Once it's short, it fast releases electricity and it creates a heating effect to 100 degrees Celsius and later about 180 degrees Celsius. At this moment, it's nearly impossible to stop the bad things happen. The battery is about to catch fire. You better run as fast as you can in order to escape this. So is there a way we could stop those, make the battery completely safe? And this has been the topic we have been trying to brainstorm for a long time. So some of the ideas I want to show you right here. For example, how do I detect that lithium metal dendrite before it shorts my battery completely? So we are thinking about putting a detector in the middle separator that can detect the dendrite halfway. What about the battery shorting really happen? You want to prevent the battery go above 100 degrees Celsius. Let's put a thermal switch inside. Working with Professor Zhenan Bao in chemical engineering, we come on a new idea how to do so. Or if it really need to go busted, it's going to be burned, let's put in some fire extinguisher inside. That's the fire retardant without impact the battery performance. How do you use a nanoscale encapsulation to encapsulate fire retardant inside the battery to make the battery safe? So idea like this, I see down the road will help the whole industry to make the batteries better and better for the wider application. So now let me also share with you in Sally's talk. Sally highlight a work done by Virtue that's very important using X-ray to look inside how the battery really works. How do we produce a battery lasting for 30 years, 10,000 cycles or longer? I mean, that has been a challenging as well. 2 years ago, we adopted this technique called cryogenic electron microscopy. This is Nobel Prize winning technique last year. Biologists developed this technique for looking at biomolecules. 2 years ago, we utilized this technique to study our batteries, to freeze the batteries to very, very cold temperature. Nothing really moved. Stabilize the whole batteries. We can look at it inside electron microscopy. This allows us for the first time to understand at the materials interface what's really there, that 20 nanometer thick layer. That determines how fast lithium can come in and go out, and stabilize the batteries. That to very large degree affecting how long your batteries can last, whether it's 3 years, 7 years, or 25 years in the future. So a technique like this, we have at Stanford building up very strong capability. These will enable us to understand this black box magic inside the batteries. So I also want to touch upon how far the batteries can go. What about the resource availability based on the lithium ion? This has been a heated topic for quite a while. So global reserve right now, that means easily mined lithium resources is about 40 million tons. What does it mean? We can make 10 billion Nissan Leaf out of that. We can make 3 billion Tesla out of that, roughly. So to consume that amount of lithium, we are still far away. So for a decade, you don't need to worry. However, for a much longer time scale, once we have a billion cars on the street, all electrical, we have grid-scale storage, we do need to consider that. Luckily, we have virtually infinite amount of lithium in the ocean, although the concentration is just too low. So recently, Steve Chu and I, we started to do a joint project. How do we get lithium out of the ocean? It looks promising. I will also encourage our young students to take on this challenge to work on this problem. Once this is solved, I think lithium, the whole industry, become nearly a done deal, but not quite. We still need to consider the availability of cobalt and nickel. You look at the price over the years, right? It go up multiple times and then it come down, right? The cobalt is $27 per kilogram. And nickel is cheaper. That's why you see the whole battery industry try to move into the high nickel and low cobalt. Cobalt just too expensive. We don't have enough cobalt to supply for the electric car. Lithium is probably not a problem, but cobalt will be the problem. So it will be even better we can use sulfur. Sulfur is virtually free. It's the side product of petroleum engineering. You want to get that sulfur out of your gasoline, it smells really bad. There's a mountain of sulfur available. People are waiting for you to take them away. So this, I think, eventually has a huge impact on the battery's cost. And also, I want to also emphasize this one unsolved problem, battery recycling. You look at all the valuable components inside. We have copper foil, we have cobalt, we have lithium, we have nickel. How do we really get all this valuable stuff out after the end of the battery life? And you look at the current process and recycling the batteries. By the way, everybody need to look at every step clearly. No, I'm joking. So this is just for showing you this is just for showing you how complex that is. Don't really look at it, but this can make you dizzy. So the battery recycling technology is not quite there yet. We need new inventions to work on these problems. So you look at all these challenges and opportunities. At Stanford, yesterday, Arun mentioned our Storage X initiative. We are very serious about that. How do we join force of academia research with industries, scale up, pilot scale testing? We want to work very close with industry to really push this forward. We have a lot of talented students right here, hunger for the new problem to work on, And we can talk about this after my talk about the storage X. So there's other batteries also out there. Let me make a brief comment and then I will end. What about solid state? Important. Solid state can help the battery become very safe without using organic electrolyte, possibly enable lithium metal by an early stage. So let's need to do long-term research to support this area. What about fast charging? We didn't mention that too much in this talk. It's very important as well. Indeed, recently, Department of Energy, the Office of Vehicle Technology, started a program of battery fast charging. Stanford team with one of the proposals in order to do so. And what about swapping batteries? That idea is still valid in some countries. This requires very strong government force to unify the standard of the batteries in order to do so. What about sodium, magnesium, aluminum batteries? These are the new chemistry, magnesium, aluminum, sodium, they're a lot cheaper. These are viable ideas. However, to develop the whole thing from the electromaterials, electrolyte, everything, we are still not quite there. Moving lithium, they're so small, lithium ions, sodium, bigger, magnesium 2+, aluminum 3+ oxidation state. They move really, really slow. We don't know how to do that yet. Require quite a bit of fundamental study as the backup technology for the future. We should support those. So eventually, coming to the grid scale, just one or two more slides is $100 per kilowatt hour. If you do seasonal storage, probably $10 per kilowatt hour or less, 30 years, 10,000 cycles. We don't know how to do that yet. So half a year ago, we published one of the paper. It's really trying to marry fuel cell on the hydrogen side. That's very robust. And the battery, that's nickel and manganese chemistry, very low cost. We realized 10,000 cycles, and particularly for the nickel system, we know it's going to run for 30 years. This type of idea might enable us to have a new solution for the grid scale storage. Let me summarize. It seems very clear to me for the mobile application, transportation is the world of lithium ion. But we still need to have a few problems to solve. For grid scale, the opportunity is wide open. There's a number of batteries chemistry promising, and also fuel cell is a strong contender in that area as well. I will end my talk right here. Thank you very much for your attention, and I will be happy to discuss if you have questions later. Thank you very much.